Hi, my name is Nicholas Wiley, and this is Material and Energy Balance, Homework 3, Part 2. So in the last video, what we did was we derived the differential equations to solve the fluid levels in the three tanks. In this video, what we're going to be doing is we're going to be simulating the dynamics of this three-tank system by using differential equations, and we're going to use solve IVP to do so. So before anything, I could just skip right into the coding, but I thought it would be important to kind of give a refresh of what we last talked about. So I'm just going to read, these paragraphs and I'm going to explain the relation to what we have on the right side, which is going to help us ease of access when it comes to coding. So we have three tanks with cross-sectional area 0.51 and 2 meters squared. They are interconnected at their bottoms with initial fluid height levels of 0.51 and 2 meters respectively. Okay, you can see this constants on the side. The magnitude of the flow between tanks, which we're going to see on the side is Q12 and Q23, is proportional to the square root of the difference in fluid heights between pairs of tanks. The proportionality constant between tanks 1 and 2 and 2 and 3 is 0.1 respectively. Tank 3 drains to the surrounding height at a height of 0 with the same proportionality constant. What all of this means, it's a lot of words for 3 sentences, but the magnitude of the flow, Q12, is proportional to the square root, which we're going to see, of the difference in fluid heights between pairs of tanks. We have the proportionality constant, which is alpha, which is 0.1, and we have tank 3 drains with the same proportionality constant. Okay, so let's kind of unpack what we saw. So we have our flow rate between tanks. It is proportional using alpha. It is the square root of the difference in fluid heights between pairs of tanks. Now you may be asking, Nick, why do we have this absolute value? Now I am no pure mathematician, but what I can tell you is that you cannot take the square root of a negative number. So what we have that absolute value for is, especially at the beginning, this is sort of drawn to scale, this is tank 2 and this is tank 1. Now if we tried to plug this in, we would get a negative number right here. H1 minus H2 would be negative 0.5. And we can't take the square root of that. So what we're going to do is we're going to take the absolute value of that difference and take the square root so that it's always positive. And then what is not shown now is we are going to have a sine function in front, which we'll get to in the code, in front of this, just so that we know if it's positive or negative, just because we can't take the square root of the negative number. It all makes sense as we go. And then Q23, same thing. Tank 3 is higher at the beginning, and we can't take a square root of a negative number, so immediately we would fail. So what we have to do is that absolute value and change the sign dependent on the difference between. And we have our Q out, which is just our proportionality constant multiplied by the tank of height 3, the height of tank 3, square root of that. All right, moving on. Using the simplest form of control for the fluid level in the third tank, proportional control, the flow into the second tank, which is going to be our Qn, is set equal to the proportionality constant, which is Kc, which we have as a constant on the side, multiplied by the difference between fluid level set point for the third tank, our H3Sp right here, and its actual fluid level, and we have that H3Sp is equal to 4. And that's all we need. Actually, in the last video, what we did was we derived these relationships. We tried to determine the flow rate between these. So we have our cross-sectional areas, which we saw up here, multiplied by our change in height. That's pretty much just going to equal the change in volume when it comes down to it, because area, meter squared, times height is going to give you volume, and that's going to be equal to the negative flow rate out of between tank 1 to 2. So in the beginning, what we have is, when we do this, we have tank 2 is going to be higher than tank 1, so this Q12 is going to be negative, and is going to be negative. It's going to be negative. So when we do the negative Q12 of this at the very beginning, it's going to be turning that negative and multiplying it by negative 1 to make it a positive flow rate into tank 1. Hopefully that made sense. But either way, these are our equations that we derived. I did it in the last video. You can always check that out if you'd like for a more thorough description. All right, so before anything, we have the import numpy as np, the classic. Numpy is our favorite. And then we have the make subplots, because we're going to be visualizing the simulation of this, the fluid levels between the tanks. And solve IVP, which is what we are going to be doing, simulate the dynamics using this. All right, so let's move on. Now, first thing I like to do is always just get the constants out of the way. So we're going to make these heights initial it's going to be used, it is initial value problem, solve initial value problem. So we need to have our initial values listed. 0 0.5, 1.0, 2.0. I believe that's correct. Yes. And since our cross-sectional areas are the same, we can just do a little change. All right, and we have that down, and alpha. Now we could do, as I might have previously stated, we could do alpha 1, 2, 2, 3, 3 for the flow out between the flow between 1 and 2, the flow between 2 and 3, but they're all the same. So for ease, we are just going to leave that as alpha. And after that, we have our Kc, which is our proportionality constant for the flow rate in, which is also 0.1, but it'll help make a difference as we write, knowing that it's used for flow in, not flow between. And then we also have our H3SP, which is going to be equal to 4.0. Now, if we just had these as 4 and there was no decimal, like I could just do 4 dot, we wouldn't be able to get flow types of numbers, so decimals. Click aside, but also, I forgot to do this before, but what we can do is we can create a time interval that we are going to use for the simulation. So we'll just say that we'll stop the simulation at 300 seconds. That should be enough time for it to get to steady state when all the heights in the fluid are steady. There's not much flow in between. It kind of just reaches a stable level where everyone's comfortable with each of the tanks. All right, and I believe that we're good to just move on into defining a function. Now, what we're going to be doing is we are going to be, we want to return this dH1, dH2, dH3 divided by dt. So what we need to do is we need to solve for that, which we need to determine Q1, Q12, Q23. So we are going to be defining our equation according to TY. We'll just follow their inputs. Now what we need to do is, since we have 3 different differential equations, we have 3 different tanks, we have 3 different heights, we need to unpack this y so that we know that. And we're going to call it H1, H2, H3 because it's going to be changing. We just have these initial values to compare to, if that makes sense. And I don't like that it always does that. And let's move on to these equations. So I'm just going to copy and paste these. I am going to have to make some changes. Done this a few times already, so I've gotten pretty used to it. Leave an empty space, you'll see why. And we have Q out. All right, so these are our 4 equations, our base relationships between heights and proportionality constants and flow rates. So let's begin. I believe this first equation is okay. Yep, that's okay. Now the second equation is where we're going to run into some issues. Now I do have brackets. We don't want to make an array. This is going to have to be np.absolute. I believe that's correct. Yes, h1 minus h2, no brackets. And instead of raise, double star, because they couldn't just make it the same. Darn new Python, and we are going to need that sine function I was discussing. And I believe that looks good. Now, I did not paste it from this side because it would just be a lot more work, so I am just going to change this, or it's going to change the 1s and 2s to 2s and 3s. Pretty straightforward. I'm trying to be quicker with this. H2, H3, square root, down here, change this. And those are the relationships that we're going to need to return the rate of change of height over time for each of these tanks. So we are going to return what I just said. So we're going to want to isolate dH1 over dt, dH2 over dt, dH3 over dt. And we're going to need to return 3 different things because we have 3 different differential equations. So let's just get right into it. Negative Q1 2. Don't believe we need brackets or commas or anything. Or we do need commas. I don't believe that we need brackets. So let's move on. I am just going to we are going to need that in parentheses. Q12 plus Qn minus Q23. Correct. Divide by Ca2. And then we are going to need Q23. Oh, what is happening? Q23 minus Q out. And again, these are what we derived in the last video. And I believe that that should work. Negative Q1, 1 underscore 2, comma, Q1 underscore 2 plus Qn minus Q2 underscore 3. Yeah, okay, that worked. I think that, as you can see over here, there's a little bold mark right here, just so that I could see the negative, but I just copied it, so I had to change that. Oh, okay, either way, let's move on. So now that we have our returned, we have now gotten these. Now what we're going to do is we're going to solve IVP, as we were clearly stated to do in the problem description. We are going to use our function is equations. Our time span is going to be from 0 to tf. And then we're going to need our initial values, which we have very clearly stated above, hi1, hi2, hi3. And then we are going to need a method, which is, I always forget, rado. It's like radius, but rado. And dense outputs. So that it is easier, dense output is equal to true. And events, vectorized arguments, I don't think we have any of those. And oh boy. Oh, I don't know why it's like that. Just had to flip that. But either way, we get all of these numbers, these arrays. Oh, so that's nice and all, but what we really want is we want this solution, because what this did was it just solved those initial value problems for us. So we are going to pull that. I'm going to pull that solution, and we'll just call this solution. Sol is equal to dot sol. So we're going to be unpacking, and we're going to be stealing this sol value, because what we're going to be doing is we are going to be, let me just condense this, it's messing with my head. So what we're going to be doing is we're going to be solving each one according to, we're going to be solving each of these. All right, let's just get right into it. I'm not very good at explaining. So before anything, we need to create our time interval, our simulation time. So we'll just call that time for simplicity's sake. Is equal to, we'll do from 0 to TF, which is 300, and we'll just do 300 even spaces. 300 spaces, oh, I accidentally said it, mb.unspace. That is going to evenly space all of those between each other. All right, and now what we need to do is we need to make values that we're going to be using for our plots, because we have this time now. We have our values for the time that we're going to be using for our plot, our x-axis. So now we need our y-axis. So what are we going to do? What we're going to do is we are going to make values for each of the things. So I guess we could just say, I'll just call it, oh, I guess it's H1, so we'll call that H1 PV, sure, plot values, H2 PV, H3 PV is going to equal a solution for each of those times. Okay, and now we have, what is it? What's the function? Make subplots. Make underscore subplots we're just going to make that a function, but we need to call this something. We like to go with fig in this class, so I'm going to go with fig as well. And all we have left to do is make these scatter plots. Fig dot add subplot, scatter plot, scatter. And we're going to need our x values, which is time, our y values, which are going to equal h1 PV. And then what else do we need in here? Let's name each of these. We're going to name this one tank 1 height. And it is a scatter plot, so it's going to give us points. So let's do mode is equal to lines. Now what we can do is we can just copy this. And all we got to do is change a couple values. Tank 3, not H1 PV, H2 PV. Nope. H1 PV, H2 PV, H3 PV, and cross our fingers, and we got it. Took a while, but I finally got it first try. So I think 300 is actually pretty good. I was going to say we could adjust the time scale, but I actually think that this looks pretty good. So we've created this, this subplot. We have effectively simulated the dynamics of this 3-tank system by solving the differential equations using our SciPy integrate solve IVP. But a big question comes to mind at first. Nick, you told us from the beginning that our set point height was 4. Why are we not at that set point? Now, what I have to say to you is all I have to say to you is that there are limitations that come from simplicity. And what I mean by that is by using these proportionality constants rather than proportional, I don't even know what you call it, like a proportional function, something that changes. When you just use a simple constant, there's limitations. It's not going to mirror real life. You're not going to be able to do everything you want to do. So by making our lives easier and using proportionality constants, that would save us a few equations. That has also not given us that desired result. And I hate to say it, but there's not much we can do about this, which is sad to say. We won't be able to get to that 4 meters just because of the logistics, just because it's not a real life scenario. We could try and change some things, like, I don't even know. We can make this, like, I don't even know, 3. Well, that did not help at all. So I could mess around. I could sit here all day and I could mess around with this, but 3 point. Maybe that'll make a difference. Put more in the first. Nope, that did not change a dang thing. So pretty much what I'm trying to say by this is I could sit here all day. I could try and change all the values just to make this get to that set point of 4. But realistically, we are limited by the simplicity, the ease of using proportionality constants. But either way, thank you for watching. I hope you enjoyed, and I'll see you next time. I hope I was recording that time.